your excuse me, your first lesson for pre-calculus for your senior year. I know it's very exciting. We got a lot of work to do between now and May of 2023, but I promise you it will fly by. So this first lesson, we're going to be talking about function and function notation, and you have your printed notes out with you, hopefully. If you're watching this for the first time or you are watching this as a review, you've already gone over it. But a lot of this stuff, if not all of it, is something that you've already done in your Algebra 1 or your Algebra 2 class. All right, so the nice thing about this course, at least for a lot of the first semester, it will feel like a review. Yes, I know some of it will be new. And again, I'm not saying just because you've seen it doesn't mean it's not challenging, but ultimately that should give you some confidence that you can have some success this first semester. All right, so let's start with this first part. So we have, for the first blank, a relation is a set of ordered pairs. So again, usually they give it to you in a table or some type of map with X and Y, but it's just a set of ordered pairs, and it doesn't have to be X and Y, but most of the time it is. The set consisting of the first components, again, usually the X, this is called the domain. Hopefully these are words that you remember from your days in algebra. And it's also known as the input or the independent variable. Now, in my stats class, for those of you that are also taking AP Statistics, we don't actually use the word independent. We use explanatory. But again, a little bit different kind of math. We're going to focus on the word independent. The set consisting of the second components of each ordered pair is called the range and is also known as the output or the dependent variable. And just like I said, the independent variable, we use the word explanatory in AP Statistics. For the dependent variable, we've used the word response variable. All right, so let's look at this. These ordered pairs here. We have 1, 2, 2, 4, and so on. So it wants us to look at finding the domain or input or independent values or variable here. So again, this is talking about the X values. So if I go ahead and do my notation here, that's 1, 2, 3, 4, and 5. And I'll go ahead and fill that in the table as well. So 1, 2, 3, 4, 5. For the output or the range or the dependent variable, right, that's going to be my Y values. So that's going to be 2, 4, 6, 8, and 10. All right, filling that in the table as well. Okay, now, if I were to plot this, all right, so I've already given you this information in a table as well as listed out. Now, if I wanted to show you graphically, I could put that on this plot here. So 1, 2, 2, 4, 3, 6, 4, 8, and 5, 10. Now, I know many of you probably are thinking, all right, let's make this into a line, right? It looks like a type of function that you know, but that's not necessary for this. I'm just going to leave it as it is with those dots. We're just trying to plot these values, okay? Now, one thing that you guys have already learned is that if you're given a relation, right, if it satisfies certain criteria, you can actually go a step farther and say that it is a function. So in terms of going from a relation to a function, all right, that means each of your outputs can only have one unique or individualized input. All right. So again, when you look at this, we'll go through some kind of illustrations of this with this mapping. But ultimately, you want to be looking at the kind of the key thing is looking to see if you have any repeats in your input values. All right. So make a little note here at the bottom of this page that if it's a function, then you cannot have repeats in the input values. All right, so that's kind of the key thing that I look at when I do this. When you're talking about that the output is a function of the input, that phrase up here in this general note, you would have probably heard this a lot in your probably even middle school days, that another way to think of it is that Y is a function of X. And again, I know you'll get probably tired of this, but it will go away soon, I promise. But a good comp for this in AP statistics is that I tell the students is that your explanatory variable, so your independent variable, your x, explains your response variable. Okay. So if you look at the mapping here, you can see in the first one and the second one that your input values are going to your output values, and we're not repeating any input values. Obviously, the middle one, this letter B, is probably the simplest because each of your inputs goes to a unique output. We'll talk about that later on this lesson, what that means. In A, it can be a little confusing, but because we're not repeating any of the inputs, we're just repeating the output letter N. That's okay. It's still a function. But as you can see in this input here for part C, right? Part C, we have Q is repeating. So if I asked you, if I said, okay, I know that letter Q is my input, could you tell me the output? And the answer is no, you couldn't, right? Because it could be Y, it could be Z. I know a lot of times in middle school, teachers would use the idea of a vending machine. I always like that in terms of my idea of a function. I know I don't think we have any vending machines at the school, sadly, but I'll give you a quick little story to age myself. I was, oh my gosh, a senior in 2003, 2004. That's a long time ago. And my high school, my senior year, got this vending machine. I thought it was the coolest thing that actually had a freezer of ice cream treats or whatever. And when you typed in the number, it would open up the freezer, the cooler, and it would like use the vacuum to like suck up which one you got or you picked and then drop it out. That was the coolest thing. But the kind of point of me telling that story is whatever number I typed in corresponded to whatever treat I wanted. So if you had your like number 15 corresponded to a popsicle, but also like a fudgesicle, that would be a problem for the machine. It wouldn't know which one to pick. So that's why I always think of vending machine as a good way to think of, is it a function or not? Okay, let's keep going. Now, the idea to decide whether a relationship is a function or not is to identify the input and output. So what are you choosing to be your X and your Y? All right. And if each input leads to only one output value, then it is a function. If any of your input leads to two or more outputs, then it's a relation. Okay. So everything starts out as a relation. So if we look at this example here of baseball players from, many years ago, Babe Ruth in the 20s and 30s. So it says, is the rank a function of the player name? All right. So when I look at this, I'm looking at my inputs. In this case, I'm talking about is my rank being my Y value and player name being my X value. I'm not repeating any of the player names, right? Babe Ruth, Willie Mays, Ty Cobb, Walter Johnson, Hank Aaron are all unique. All right. When I look at the part B, is player name a function of the rank? All right. So then I change my input to be rank 1, 2, 3, 4, 5. And again, all of those are unique. So I'm not repeating any. So both of these are actually functions. All right. So no issues with A and B being relations. Let's talk about another kind of example here. If you look at determining if class grade rules are functions. So this is probably pretty appropriate for you guys right now. I'm sure our numbers are a little different. I know they are than this table. But you guys, as being people who are students who are applying to colleges, for this semester or during this semester, you are obviously very intimately aware of what your grade point average is. So in this case, when we're looking at this table, I could ask the question, is GPA a function of percentage grade or percent grade? Okay, so when you look at this, all right, we're looking at, is your GPA a function of percent grade, where your percent grade is your X. All right, so if I like pick a random percentage and say like 73, all right, if I tell you the input is 73, could you tell me my grade point average component that I earn for that 73? And you could, right? A 73 earns me 2.5 in terms of my grade point average, or my grade points, if you will, because not an average. Okay, so you do that for all your courses. That's how you get your grade point average. So this is yes. All right, so if I were to choose 87, all right, I would earn 3.5 grade points. All right, it's very clear that when I tell you my input of a percent grade, it's very easy to tell me my grade points that I earned. All right, let's go the other way. Let's flip it. Is percent grade a function of GPA? Okay, so now when I look at GPA, which is now my input or my X value, if I tell you that I earned a grade point of 1.5, could you then tell me what percent grade corresponds to what grade point average that I earned? And the answer is yes and no. I mean, it's really going to be a no. I mean, you could tell me it's 62, 63, 64, 65, or 66. But because you can't tell me exactly which one it is, all right, that means it's not going to be a function. Okay, so the way you could also visualize it is if it were a table, you'd have 1.5 on your input, 62 on your output, 1.5 on your output, 63 on your output, and so on and so forth, because you have to repeat that 1.5 because you have multiple outputs it could go to. So in this idea, is percent grade a function of GPA? The answer is no. Okay, let's talk about function notation. There's a lot going on here, and as I'll explain throughout the course, I'm getting all these materials from our textbook, which is a free textbook on this website called OpenStax, and I'll put that in the syllabus. You can always check with that. But everything here, if you want to read through it, is all coming from the textbook. So you can read it here, read it in the textbook. It's your choice. I know in my experience, personally with math classes and with students that I taught for a long time, is that most students do not particularly read the textbook in math, and that's fine. I didn't really start reading my textbook until probably junior, senior year, and then into college. But I highly recommend it for anyone that's interested in kind of building that skill, to take a moment to go see what it's like to read this in a math textbook. Okay, so we've done this a couple of times in your high school career, but essentially when we talk about your function notation, right, and it is a big deal because if you are given a problem or given any type of information about something you're trying to work with, the moment you see that function notation, we've always used f of x. And I've told you to think of that as the same as y. And I know it's not exactly the same as y, right? I don't need any mathematicians making comments here because it is not the same, right? Y just denotes a relationship. But if I tell you it's f of x, I'm telling you that I have checked and it is actually a function. So no worries on if it's a relation or a function, okay? So just keep that in mind when you're doing this, all right? That is specific for when it is, in fact, it is a function, okay? Now, let's look at a few examples here. So this next one says a function n equals f of y gives the number of police officers n in a town in year y. What does f of, and a key thing, I know you guys are not going to have any issues with this, right? That does not mean multiplication. It means f of 2005 equal 300 represent. Okay, well, y, right, f of y is year y. So when it says f of 2005, that's saying in the year 2005. Okay? And then equals 300 is equal to my capital letter N, which is the number of police officers. So in the year 2005, there were 300 police officers in this town, whatever this town or wherever it might be. Okay, let's look at letter D. It says use function notation to express the weight of a pig in pounds, which I'm going to choose to be capital W, all right, as a function of its age in days D. All right, and it's telling me to use lowercase d. So we have weight, all right, which is capital W, equals the same as the function of its age. So here's the function notation in days, letter D. All right, so that's kind of the expression that I want you to become familiar with. Not something that you've necessarily worked with a lot in algebra, but make sure that you are aware of how to do this. Okay. Okay, so now let's look to see if in these tables, Do they represent relations or functions? Remember, everything is a relation. We're checking to see if we can go that additional step to say it is in fact a function. So the fastest way to do this, or the most efficient way to do this, is to check the inputs. So in table 1, the inputs are 1, 2, and 3, so I don't really care what all the outputs are because the inputs do not repeat. I know that this one is a function. Table 2, we have 3 unique inputs. I know the outputs have a repeat, that number 5, excuse me, but because the inputs are all unique, this is also a function. And finally, the last one, we have a input that is repeated, that 5. So if I input 5 into the function, could you tell me what the output is? No, you could not, because it could be 2 or it could be 4. So because our input is trying to map to 2 different numbers, that is a problem. So this is not a function. We call it a relation. Okay, now on the next page, all right, when we know an input value and want to determine the corresponding output value for a function, we evaluate the function. And I try my best, especially when I used to teach Algebra 2, but I really want your brain, especially when you leave this school, to understand the difference between the words like solve, evaluate, simplify. So it's not, again, anything that you're doing wrong, but let me go back. You are doing something wrong if I do this, but I'm going to correct you if you use one of those words incorrectly or in an inappropriate time. Like I'll get students so many times that'll say, how do I solve this? And there's not an equal sign. So if there's not an equal sign, you're not going to be solving anything. Okay, so make sure, just keep that in your back of the mind. I'm just trying to help you guys understand how to speak in this language of mathematics. Okay, now when we want to go the other way, when we know an output value and want to determine the input values that could produce that, we set the output equal to the function's formula, and here's that word again, and solve for the input. Okay, so let's try this with a few of these here. We've got a function, which I know some of you out there are very happy to know that this is one of your favorites, the quadratic trinomial. And we're going to evaluate this function 4 different ways. Okay, the first way is probably the simplest way, which is f of 2. So let's use letter A, which is f of 2. So I'm going to replace x with 2. And as you've been doing for many years, make sure you do this with parentheses. Okay, so that's going to be 4 plus 6 minus 4. And if you go left to right, I mean your answer is going to be 6. So A is f of 2 equals 6. Let's do letter B. Okay, so letter B says to evaluate this function at letter A, so f of A. So I'm going to replace my parentheses with A. Okay, so that went into all of my input values, my x, and it becomes A. And so actually, because this is a different letter or variable, I'm going to leave it as a squared plus 3a minus 4. So this is the answer for f of A. Okay, let's try letter C. Letter C says to evaluate a plus h. Okay, so it's each time gets a little bit more challenging here. All right, so I'm going to plug in a plus h where it says x. Don't forget those parentheses again. Okay, now the first thing I see is I need to expand a binomial squared. All right, you've hopefully been doing this for a while, and I'll show you in class, working it out by writing a plus h times a plus h. But I hope at this point, you guys are 17, 18 years old, I hope you're ready to just do this mentally, where you square the first one, you square the last one, but the middle term is your 2 terms multiplied by 2. So you have a times h times 2, which is 2ah. Okay? Distribute that 3. And you're actually finished. There's nothing in here that can be simplified in terms of like terms. So this is this is letter C, f of a plus h. Now let's do the last one. The last one is definitely the most complicated, but luckily we've already done a few of these pieces, right? The problem helped us with finding letter B and C first. So it says f of a plus h minus f of a all over h. And if any of you end up going into calculus next year in college, you'll recognize this, all right? Something you're going to be talking about called the difference quotient. You don't need to know that for our class. All right, but if you're wondering, like, where did the textbook decide to do this? Like, what? That's where it comes from. It's something you use in calculus. So we're going to write down, this is f of a plus h, which is a squared plus 2ah plus h squared plus 3a plus 3h minus 4, and then minus this f of a up here, this letter b that we did, which was a squared plus 3a minus 4 all over, don't forget the fact that it is a quotient, right, division, all over h. Now, you could take that negative sign and you could go ahead and distribute it if you want. I noticed that we're going to be subtracting things that are the same, like a squared minus a squared, 3a minus 3a, negative 4 minus negative 4. So all three of those are going to make 0. So that leaves me with 2ah plus h squared, plus h squared plus 3h all over h. Now, again, everything we do after this is not, you're not really going to see the importance of what I'm about to do until you get to calculus, but at this point you might notice that in our numerator, all three terms do have an h, which I can factor out to get 2a plus h plus 3. And then we have h now divided by h, which is going to cross out and just leave you with 2a plus h plus 3. And wherever you are, when you get to this place in calculus, if you take it, you might think, oh man, I remember when we did that in Mr. Vander's class. Okay, so that's it for this page. Let's move on to the next page. Now, on this one, all right, when we're talking about evaluating functions expressed in function form, all right, we're going to do this a couple different ways. We've already done it algebraically. We'll show you using tables. We'll also do some graphs. All right, but ultimately, I'm not that concerned because you've been doing it for a long time. All right, in terms of these next few questions, they might seem a little bit different to the ways you did it in Algebra 1. That's okay. But we're going to give a function. They're going to give us a function that's written in equation form, and we want to write it in its algebraic form. So look at letter A, for example. It says to express the relationship 2n plus 6p equals 12, all right, as a function, p equals f of n if possible, if it's a function, okay? So the way I always think of this is when you look at it, we want to figure out and solve for that letter p, all right? So I'm going to isolate for p, which means to move the 2n to the other side, which gives me 6p equals 12 minus 2n. Okay, then I'm going to divide both sides by 6 and get p equals 2 minus 1/3 n. Okay, now at this point, this is what we would call p in terms of n. Okay, or another way to think of it is p written as a function of n. And when you look at this, right, when you look at that, you should see that it is a function. All right, in terms of looking at n, that's n to the first power. This is just a linear function. So I am going to use that function notation that they wrote here, f of n, to replace p. So f of n equals 2 minus 1/3 n. Okay, I think what can be a little confusing here is that you're so used to working with x and y, all right, that you might have a little trouble about what to do or which letter to kind of work with. All right, but hopefully you'll see if it helps. If you need to think of this as y equals f of x, you always can, right? And that should make it a little bit simpler. Okay, let's do letter B. Does this equation, x squared plus y squared equal 1, represent a function with x as the input and y as an output? So if so, express the relationship as a function y equals f of x. So I'm going to solve for y, so isolate for y. So y squared equals 1 minus x squared. Then I need to take the square root of y squared, and I need to take the square root of both sides. So that gives me y equals plus or minus the square root of 1 minus x squared. Okay, now you may not recognize this, and that's okay. This is not something that you necessarily remember from your days in Algebra 2. We'll get there in a moment. But when I look at this, if I were to plug in values for x, that would be okay to use. I can plug in 0, right? 0 squared is 0, 1 minus 0 is 1, and the square root of 1 is 1. But when you plug in 0, you get two different numbers, right? You get positive 1 or negative 1. And we said from the very beginning of this lesson, if you take an input and it gives you multiple outputs, then that means this is not going to be a function. You're repeating your inputs. You'd have to have 0, 1 and 0, negative 1, which would be an issue. Okay? So actually, this is not a function. All right, so this is a relation. All right, so I cannot write this as a function. And some of you may have recognized from the very beginning, it's okay if you did not, that this right here is our equation, a basic equation for a simple circle. All right, so let me kind of put all this together graphically. I know some of your brains, if you see this visually, it might be easier to notice. So I'm going to go to Desmos and graph this square root of 1 minus x squared so you can see what it looks like. All right, so we have the square root of 1 minus x squared. And I also have the opposite of that. Right, I have to do the positive and the negative. And sure enough, when you put the purple and the black together, let me zoom in a little bit. When you put purple and black together, you get that circle. So I told you this x squared plus y squared equals 1 is that circle. So you can see the red just is over that purple and black. So I take it away, it's there, and back and forth. Okay, so you get the idea that this, even from the get-go, I would have known that this is not a function because it is a circle. Let's try letter C. If x minus 8y cubed equals 0, express y as a function of x. So again, I'm going to solve for y. So I'm actually going to move the negative 8y cubed to the other side just because it's already a negative. When I move it over, it becomes positive. Okay, divide both sides by the 8. Get 1/8 x equals y cubed. You know I cannot leave that cube there. I got to move it to the other side by taking the cube root. So I have the cube root of 1/8 x. Now I actually know the cube root of 1/8, right? The cube root of 1 is 1, the cube root of 8 is 2. So I could actually rewrite this, it doesn't matter, as the cube root, as 1/2 times the cube root of x. All right? But the thing I'm asking myself is, do I think that this is a function? All right, we'll talk at the end of the lesson how I kind of know this stuff. You can ignore the 1/2 if you want. All right, but when you think about graphing the cube root of x, right, I know what that looks like. I know that the cube root of x is going to look like this when I graph it, which is a function. So this y is a function of x. So I can go that step farther and write this with function notation that f of x equals, and I'll make it look a little nicer, the cube root of x over 2. Okay? All right, so now let's go ahead and look at different ways, like with tables and with graphs, to figure out when things are, to evaluate those functions. All right, so you can read all the steps, but I think we can do this pretty straightforward. It says use the table, evaluate g of 3. So g of 3 means my input, all right, my input, which is n, these are my inputs. When my input is 3, I get an output of 7. All right, so that one is done. All right, now letter B, just going backwards. You look at your output being 6. So find where your output is 6, which is here. What are the inputs that would work for that? And the inputs would be n equals 2 or n equals 4. And so some students might think at this point, wait, I thought you said it was a function you couldn't repeat. But again, look in the table and see what's repeating. What is repeating is actually your outputs, which is okay. The things you cannot repeat are your inputs. All right, let's do the same thing with a graph. All right, so I like to do it where if it gives me the input, that -1, I go to -1, which is right here, and I plot that point. And what is the y value when I plotted that? It is 4. right? For letter B, I'll use a different color here. I'll use green, right? When I do letter B, and it tells me that f of x equals 1, I know that f of x and y are the same thing. So I'm going to plot that line y equals 1, which is a horizontal line. And where does my function hit that line? At 0, 1, and 2, 1. So the x values that would work would be 0 or 2. All right, and that's a strategy I'm sure you've used in the past. All right, almost there, guys. We're very close. All right, so the next one is talking a little bit. We're going to talk about the vertical line test, the horizontal line test, and then eventually you'll see right here functions that are one-to-one. So one-to-one functions, that means you have only one output for each, only one input for each output value. So in this case, it's like a special case function. So we've gone from relation to function, and now a one-to-one function means that you only have one input for each output. So you have unique values everywhere. All right, so nothing repeats. So this is a one-to-one function. All right, and you'll see later how we can test for that. So if we go back to the idea about the percent grades to a letter grade as opposed to a GPA, same kind of deal, right? If each percent grade earned in a course translate to one letter grade, is the letter grade a function of the percent grade? So essentially, if I tell you, all right, that I got an 86, all right, can you tell me what my letter grade would be? All right, in this school, I could be wrong on this. I think that's a B plus. I'd have to go check with our college counselors. All right, but the idea is yes, this works. If you give me an input, which is a percent grade, all right, so in our school, we're looking for something hopefully in the 90 to 100 range. I can tell you what your letter grade is. Is this a one-to-one function? All right, so is this going to be where if we have our inputs, are they unique inputs for each output? All right, and the answer is no here. All right, and here's how I would explain it. All right, if you tell me you got a 91, but then your best friend got a 92, right? Yes, you guys, it is a function, so you guys got A's. You're not repeating any of the inputs, but because the output, that letter A that you both got, is being repeated, that means it is not one-to-one. All right, so just be careful as you're going to that next step. Now, you've been using the vertical line test probably since you were in 7th grade. All right, so the vertical line test can be used to determine graphically if a relation is a function or not. So as long as when you take your pencil or your pen and you move it from left to right across your graph, as long as you only cross one point at a time on that vertical line, it will be a function. So they've given you a few examples here. And the first one's a function. The second one is not a function. That would be taking like your parabola, putting it on its side. And then again, we talked about a circle. This is not a circle, it's an ellipse, very close. All right, so that's not a function as well. Okay, so we can do a quick example here. Does this graph represent a function? The answer is yes. Is this a one-to-one function? All right, and the way to do this is actually with what's called a horizontal line test over here. So the horizontal line test, all right, is where you take your pen or pencil, flip it to be horizontal, and if you find a place where it hits more than one point on a horizontal line, like right here, then it fails the horizontal line test, so it is not one-to-one. All right, and as you'll see in a moment, this letter V that we've just looked at is called an absolute value function. All right, so the absolute value function is not one-to-one. Now, the very last page that you have for your notes, I'm not going to write anything on it. Just take 30 seconds to just show you what it is. This is a list of all the parent functions that you have talked about in your career so far in terms of your math. All right, so if you're not familiar with these, make sure you get familiar with them. I think you probably are familiar with most of them, but just make sure you look at them. It's going to help you so much if I show you what this graph is and you know what parent function is coming from, and vice versa. If I tell you here's the function, could you sketch a basic graph of it? Okay, so that's it for the first lesson. It's going to be a great school year. Good luck.